Okay, my presentation is about ionospheric scintillation effect on GNSS. Basically, I will show an introduction to ionospheric scintillation. I will discuss some mechanism for generation of equatorial scintillation. I will show some measures that show the effect of scintillation on GNSS signal. I will present a statistical model of scintillation. I will show also a cost loop that is a kind of system for recover the phase of GNSS signal in the GNSS receiver. And at the end, I will present some conclusions about okay. Ionospheric scintillation are rapid fluctuation in the amplitude and in the phase of trans-ionospheric signal. This distortion are caused mainly because irregularities at the electronic density by the signal pass. Another information, the scintillation is more intense in the region around the magnetic equator and also in the polar regions. In fact, the scintillation near the magnetic equator is called equatorial scintillation, and it is completely different in terms of mechanism, frequency, than the scintillation in high altitude. The problem is the scintillation affect strongly the communication in several bands of interest, namely in VH band, VHF band, and UHF band, that the band where operate all the GNSS system. Another information, the scintillation depends on the season and depends also the 11-year solar cycle. Then the scintillation depends on several parameters. Okay. Well, to start discussion, I will show here the ionospheric layers. In fact, the ionosphere starts at about 50 kilometers and it goes up to about 1,000 kilometers. Then it is classified by several layers. Depend on the height, you have different electron density. For us, I mean, in equatorial region, the big problem is this layer called F layer. In fact, we will see the equatorial scintillation is due to the irregularities in this layer, in this F layer. It's interesting to observe there is a difference in the electron density if we compare the profile during the day and during the night. During the night, you can see the F layer is strong, but for example, the irregularities or the electron density in E layer decreases very much. You see, you have two orders of in the electron density. Here we have the frequency of scintillation by the geographic regions. You can see in red, the scintillation is very frequent. Exactly in this region where we have the equatorial scintillation. Observe we have a deviation between the magnetic equator and geographic equator in this region near to Brazil. For this reason, probably the Brazil is the region in the Earth where the scintillation is more frequent. Okay. In this slide, I show the profile of solar activities starting to the year 2010 up to 2040. Now we are around here. We are near to the minimum of solar activity. The next maximum will be about 2025 year. Okay. In this figure, the intensity of solar activity is measured by the radial flux in this length of wave, 10.7 centimeters. Okay. In this figure, the red is predicted value. The blue is the smoothed value monthly, and in the black is the real value measured at months. Okay. Then I mean we have to be worried in next years because the solar activity is increasing. Well, now I will focus in the equatorial ionospheric scintillation because is the scintillation we have more interest considering we are in Brazil. This scintillation has some particular characteristics, like it usually occurs after sunset. During the daytime, normally we have scintillation. The scintillation appears only after the sunset. And in this case, the irregularities in the ionosphere is due to some plasma bubbles. Plasma bubbles are regions, big regions, where the electron density is less than the rest of ionosphere. Another interesting characteristic of this scintillation, the intensity increase with the magnetic latitude. And the maximum intensity we find in the crest of the anomaly. On the other side, near the equator, the intensity is low. This scintillation depends on the season, and the frequency is greater at the equinox, exactly on September and on March. The equinox is the time when the duration of days is equal to the duration of the night. At the end, the intensity of this scintillation depends on solar activity also. When you have solar activity strong, you have more strong equatorial scintillation. Now I will talk about this equatorial anomaly. The anomaly is characterized because we have maximum ionization at about minor plus 20 degrees of magnetic latitude, and we have the minimum ionization at the equator. You saw in this previous slide exactly the problem of anomaly. Around the equator, you have low ionization, and maximum ionization is at about plus or minus 20 degrees. Okay, the question is how this anomaly is formed. Here I try to explain how this anomaly is formed. During the daytime, the plasma generates at the equator rise due to the magnetic and electric fields that actuate at the plasma. Then the plasma rise. This happened during the day. After sunset, this plasma stopped to rise, and they move along the lines of magnetic field. And at the end, this density intensify exactly at about plus minus 20. After sunset, there is no the action of the sun. Then it started the recombination between the ions in such a way that in the E layer creates a low density layer. Then we have a low density layer together high density layer, and due to the instability in this plasma, this instability is called Rayleigh-Taylor instability, creates plasma bubbles in the base of F layer. These bubbles represents the irregularity that distorts the GNSS signal. Okay. This scheme I will show the process of generation of the equatorial anomaly. About the equator, we have the ionization that produce a lot of plasma. This plasma rise. during the daytime. At sunset, they stop to rise and move along the lines of magnetic field. And at the end, we have more concentration of plasma about this region. And after sunset, like I mentioned, I have a low density layer together with high density layer, and the bubbles is generated. In this slide, I try to illustrate this phenomenon. Here we have low density, high density. We have a disturb. This disturb has evolution like this, and finally we have a big plasma bubble. This plasma can have about 100 kilometers, and these bubbles move from equator to high latitudes, magnetic latitudes, both in both sides, north and south, about the magnetic equator. This figure was took at this date and show the electronic density above the Brazilian territory. Then this line means the magnetic equator, and we can observe symmetry between this line. Okay. It's interesting to observe density in these regions is low than the rest. Probably here we have bubbles of plasma. Okay. Then if you have communication from any station and satellite, and you cross a bubble or cross a bubble and other region with greater electron density, clearly the signal passes through several irregularities, and you will have scintillation. This slide show more detailed what happened with the radio wave. Let's suppose we have a plane wave. I don't know if everybody know. A plane wave is characterized to have a constant phase in all the plane. Okay. When this plane wave pass through the parts of ionosphere on where we have irregularities, the phase after this layer is not more constant. Although the amplitude remain constant in the plane, the phase is not constant. By the process of propagation, I don't know if you know the Hughes principle to generate wave. If you have a plane wave by the principle of Hughes, you can see a plane wave in vacuum generate a plane wave forever. But if if we have a fluctuation in the phase in this plane, as long as the front of wave propagate, the amplitude is changing. The result is when the front of wave stay at ground, the amplitude is fluctuating like this. The problem is worse thinking the receiver in the ground is moving, and also the satellite in sky is moving also. Then all these effects together appears to the receiver exactly the scintillation we can measure. This slide shows the multipath due to the scintillation. In fact, in this picture, we show only reflected signal, but also there is some portion of signal that is diffrated. In fact, it has two phenomena, diffraction and refraction. All these phenomena generate new paths, new rays, in order that at the receiver we will receive part of signal that came directly from the transmitter. We call line of sight signal. With several rays that came from different directions that form what we call multipath signal. This multipath signal may be different phase, and when we add all this signal, you would have a big attenuation or some gain. Okay? Depend on the configuration of phase we add the signal. This slide shows a measure made in a station in São José dos Campos. Was measured signal from two satellites, the PRN7 and PRN8. One signal from one satellite, there is no fluctuation in the magnitude. The other one has big oscillation in the magnitude. We can see we have oscillation at about 30 dB, for example. This one, the oscillation was about 30 dB. 30 dB, I don't know if you know, means 1,000 less than. In fact, it's a very big attenuation. Okay. And this measure was a real measure made in São José dos Campos, Brazil. Here in this slide, I show the fluctuation at amplitude and the fluctuation in the signal phase also. Okay. Clearly, this distortion in the signal must have some consequence in the signal. Frequently, we can have loss of loss in the carrier recovery loop at the receiver. We have degradation in the measure of phase and delay. Considering that during the reception reception, we have less satellite available to do the measure, surely we have a reduction in the position accuracy of the system. In Brazil, for example, it can cause disruption in some cells like precision agriculture, offshore operation, navigation. Another consequence of scintillation in Brazil, the system GBAS that supports civil aviation is not available in Brazil because it's not feasible to use this kind of system.
After sunset. After sunset.
Yes, after.
In the middle of the day, it's more or less okay.
Yes, yes, yes.
But if you use the GBAS, you need to attend to the requirements, and you need guarantee 99% of the measurements in the day, in the variance. Because of it, you can apply this one. Yeah, because it's about the entire day.
You put 99% of half a day.
Okay. Usually, we characterize the scintillation intensity with two indexes. One related to the amplitude. This index is called S4. In fact, it means the normalized standard deviation of the intensity of signal. We define intensity like the square of magnitude of received signal. We said the scintillation is low level if S4 is less than 0.3. Between 0.3 and 0.5, we said this moderate level. But if this index is greater than 0.5, we said we have high level of scintillation intensity. The second index used to measure the intensity of scintillation is the index called sigma phi. The sigma phi is related to the fluctuation in the phase of signal. In fact, it represents the standard deviation of the phase fluctuation directly. I show now some measured results made in station in Brazil. In this slide, we saw measurement of S4 index made in several cities: Manaus, Cuiabá, Cachoeira Paulista, and São José dos Campos. All this measure was made in this date, 21 November 2001. It's interesting. Here we have several satellites. It's interesting to observe, for example, in Cuiabá, at this time, all the satellites present strong scintillation. You see, during all this time, 22, 24 local time, the value of S4 was greater than 0.5. Okay.
What's this pointed line?
In fact, I don't know.
Okay.
In the text of the author, he don't explain what it is.
Okay.
It's probably the satellite elevation.
This dotted line maybe the reference. This is the reference and how this is moving above and below.
Okay.
Yes, you said
Yes. Good. But the author don't explain.
Yeah, I think it's probably the satellite elevation.
Elevation.
On the right-hand side of the
Right.
plots is 0 to 90. It's elevation.
The elevation is greater than 20 degrees.
Yeah. This is the elevation
Yes,
goes from 0 to
yes.
90, 0 to 50, 0 to 50, and this is these lines here. And on the left-hand side, we have the S4 index values from 0 to 1.
Okay.
I think
He explained it precisely. Okay. In fact, it's the elevation.
yeah.
Okay. Here we have some mesh in Fortaleza, done by your GPS.
Yeah.
Then we have mesh made in December of 2015 at the days 15 up to 26. We can observe at about midnight we have a strong scintillation all the days. The level is greater than 1 in some case. Okay. In this graph, we show the magnitude of magnetic field. Then, at these days, we have a storm, a magnetic storm. The interesting phenomenon is the magnetic storm change the pattern of scintillation. In these days, we can observe we haven't scintillation at night due to the magnetic storm.
It's very curious.
Yes.
Very curious.
Yes.
It's anti-correlated. Mhm. The scintillation in the equatorial is very different from the equatorial.
Yes.
The scintillation in the aurora and
Yes.
high latitude.
Even the statistics of amplitude and phase is completely different. Here we have one more measure. This measure was made in São José dos Campos in this date, and we have the magnitude profile for three frequencies, L1, L2, and L5. We can observe that for L5, in average, the scintillation is more strong than the rest, because the L5, the frequency is lower than all. Okay. On the other hand, the L1 is less susceptible. Well, now I will show the statistical model for scintillation. In fact, there is several statistical models for scintillation. I will show this one because this model is very simple and easy to implement. Okay, the received signal may be modeled by the transmitted signal multiplied by stochastic process I call CT that is caused by scintillation. These terms concern the thermic noise, the Gaussian noise. Then the scintillation may be modeled like a flat fade and can be modeled like this equation. We have a constant term and you have another stochastic process. Being this stochastic process, a complex Gaussian process. Okay. This constant parts may be associated with the part of signal that came to the receiver by the line of sight. Okay? And this part can be associated with the part of signal that we have refraction and diffraction. Okay? If using this model is easy to show that the probability density function of the magnitude of the process CT is given by this equation that represent we call Rice distribution. Okay, in this equation we have this factor K that is related with the S4 index. Okay, this model is very simple, but it agrees very well with the empirical data. Here we have a comparison between the Rice distribution we have presented with, for example, Nakagami M distribution. This in black, solid line in black, is empirical data. You see, it agrees very well. And this last thin line is the probability distribution considering this model, the phase screen data. Okay, this result justify the use of this model. In fact, there is several new research that point another models, but thinking in terms of engineering, in terms of project a system, this model is very interesting because it's very easy to synthesize the signal. The process DT has a given autocorrelation function that is given by this expression. There is an important parameters tau 0 that means the correlation time of the process. This process can be obtained passing white Gaussian noise by a Butterworth, low pass Butterworth filter. Here I show the power spectral density of the process DT. We can observe here is my power spectral density. This irregular curve is the empirical data. And also we compare with Gaussian. If we use a Gaussian correlation, we have this, okay, but we saw that the model agrees very well with the empirical data also in terms of power spectral density. Here I show a single mechanization of this model. We need only to have two sources of white Gaussian noise independent Then we generate the complex process at this point and pass through this Butterworth filter. And finally, I add the spectral portion, and we have the process CT. Okay. Only to illustrate the problem of scintillation, I show in this slide a classical method to recover the phase of the carrier in the GNSS receiver. It's called Costa's loop. Okay. Classically, the GNSS receiver use this configuration to recover the phase. Okay. I do some simulation using the Costa loop with these parameters. Noise bandwidth equal to 10 hertz. The relation carrier power by noise density at 30 dB hertz, and as for index 0.5, that is not a very great value. But even with this value, observing the graph of recovered phase, the loop recovered very well the phase, but at this point we have what we call cycle slip. At this point, the Costas loop lost the synchronism. Then we have this jump in phase. This jump is enough to make the system to lose the phase synchronism. Note, I make the simulation only using S4.5, but I show you it's common. This value here in Brazil reach values greater than 1. It's really critical for the system. Well, main conclusions. Scintillation occurs in equatorial and high latitude regions. It depends on geographic position, depends on the frequency, solar activity, season, time of day. Mainly, it distorts the amplitude and phase of signal that through the ionosphere. We can model the channel using supposing a rise channel. The scintillation mainly affect the carrier phase carrying the receiver. It's the subsystem of receiver more sensible to scintillation. Surely, it reduces the position accuracy for several reasons, and depending on the intensity, it can lead to complete interruption of some service. Okay. Well, if you have any question, please.
As you have one question. First of all, thank you for the nice presentation. And the question is about this. It depends on the signal frequency. So it means if you go higher frequency, then there is more. The effects is more strong.
Yes. When you increase the frequency, the intensity of scintillation goes down.
Okay.
For example, in X-band, we don't worry about scintillation. Here, our receiver have signal in S-band about 2,000 gigahertz and X-band about 8,000 gigahertz. We don't observe scintillation X-band.
Then you said that this can be modeled as Rice channel. So it means that there is only one dominant path. There are no multi-path. Multi-paths are gone.
Sorry.
When you say about
Okay.
when you say about that the communication channel under scintillation can be modeled as Rice channel.
Yes.
So it means that then there will be only one strong path. The weak path will be automatically gone. You understand?
Please, in Portuguese, please.
Please, Português, para
Como que você falou aqui, né, que esse canal de comunicações.
Isso eu entendi, só não entendi o resto da pergunta.
Oh, mas quando você usar o modelo
Do Rice.
do RAI, ele significa que você tem path, mas tem mais poder, mais dominant.
Não.
Domínio, né? São ou mais poucos. Esse é o indicador, né? Rice, canal.
Rice você tem uma parte que é especular,
Sim,
que é determinística, e você tem outra parte que é com multicaminho,
Sim.
certo? Que é gaussiano.
sim.
Nesse modelo eu posso balancear como eu queira. No extremo, sem nenhuma parte, né, de linha divisada, o meu RISE vira um RAID.
Tá certo.
Então o meu modelo contempla isso tudo.
Ali é RISE, né?
Sim.
Does the cluster loop perform both the acquisition and the tracking?
No, in fact, this data is only for tracking.
Only for tracking.
Yeah. In fact, there is some effect in the acquisition. I don't know what is the effect.
Ok. Então, um modelo de 2 raios. Pode haver mais raios.
Sim.
Um caminho óptico. Esse é um modelo mais simples.
One thing, important thing is the model, the fade is flat. It's not a selective channel.
Yeah.
This results it's simulated or it's real results?
The last figure is simulated.
It's simulated. But in a real environment, we need to have both acquisition and tracking.
Usually you are not interested in acquisition because the communication is continuous.
Okay.
Thank you very much for the presentation. It is very, very informative with very intuitive ideas.
The problem is my English.
The communication channel in English is working very, very well. No scintillation here. Still not sunset. All of the references
Yes.
are papers
Yes,
or
and
master
I
theses.
I have all the references.
Perfect. Very complete.
This reference is from the group of our colleague.
Yeah, I work with 80% of this person.
Okay.
Moraes, Alisson de Oliveira, it's very, very good paper to read. It's very complete and explain a lot of things about it.
This guy is from INPE, Eurico.
Yeah.
This is the model of
Yeah.
Father.
The first one is this guy developed the scintillation model.
Okay.
But Alisson use another model.
Yeah. Alisson used the other type of
Statistics, yes.
It's
Alpha mean.
yeah, that's it. It's very, very good. He proposed this one.
Yeah. But it's not easy to implement.
Yeah, I know. but work more better. But
In
it's
some
hard
case, in
to.
some case.
Yeah.
Okay. Well.
Thank you very much.
If you want, we can go to see the digisolar.
Yeah.
Okay.
Yeah. And the magnetometer, no? You have
Yes,
also
yes,
a
yes.
magnetometer.
Yeah.
It's a very unique piece of equipment.
Okay.
Okay, thank you very much.
Thank you.
Thanks, your very nice presentation.
Mas eu vou indo. Professor, valeu aí, cara. Oi, senhor. Aí, toma aí disponível. Qualquer hora,
Tá, Jorge.
vou falar de nós
Vamos
estamos
lá?
nessa probabilidade. Valeu.